everyone, and welcome to the Joy of Abstraction book club for chapter 7. Thank you very much for joining us, and thank you to everyone who has submitted very interesting questions, or indeed who is just following along and reading the book and remaining interested. And of course, thank you to the Topos Institute for hosting and sorting out all of these questions and videos. I'm finding it very interesting to see your questions and think about them. So thank you again. So this chapter is about relations, and we're just leading up to the definition of a category that's going to happen in the next chapter. So the first question, let's jump right in, is, could you please say something more? This is about page 83. Could you please say something more about what would happen if anything failed to equal itself? So I said near the bottom of page 83, if anything failed to equal itself, then all sorts of weird things would happen. And in the footnote, I said, in fact, everything would probably equal 0, in which case everything would equal itself. We'd have a contradiction and the world would implode. So it's very difficult to think about anything not equaling itself. And I suppose if something didn't equal itself, I think that my thinking in that footnote was that if it didn't equal itself, would it equal something else? And if something equals something else, then it might cause everything to be 0, because for example, if 1 didn't equal 1, then what does it equal? Does it equal 2? If 1 equals 2, then you can quite quickly deduce that everything equals 0 if you have subtraction, because then 1 equals 0, and if 1 equals 0, then 2 also equals 0, and 3 equals 0, and then everything equals 0, but then 1 does equal itself because everything equals 0. So it's not a very coherent thought, because it really is difficult to imagine a place where something doesn't equal itself. And I think that's because it's inherent to the notion of equality. And I have a feeling this may be related to how type theory gets started. I actually don't understand type theory, but the fundamental thing is identities, because you just start with the fact that things equal themselves. Anyway, I think that is all I have to say about that. I'm moving on to the next question. Page 83 and 93. The example about being more or less the same as something else in things to think about 7.1, right? Can you think of a way of saying two numbers are more or less the same? And then I come back to that on page 93, where I say, can you make a definition of more or less the same as? That is an equivalence relation. And so this question says, can we make it can we say more or less the same as to mean within epsilon of each other for any value of epsilon, for all values of epsilon greater than 0? So this seems to be saying, what if in what I said is, if we pick some small epsilon like half and declare that things are more or less the same as each other if they're within that epsilon of each other, then it's not transitive, because you can have this thing being within epsilon of that one and this one being within epsilon of that one, but then the end ones are only within 2 epsilon of each other. And so this question is saying, what if we let it be any epsilon, all epsilons? So it would then be an equivalence relation, because everything would then count as more or less the same as everything else, because there's always an epsilon such that the two things are within epsilon of each other. But then we're just declaring everything to be the same as everything else. That is an equivalence relation. I would say not a particularly illuminating or useful one, because we're really just declaring everything to be the same as everything else. But it is valid. So yes, I suppose. Okay, page 84. Thank you for giving us a cool symbol for relations, the box with a curved part on the end. This person says, I read things aloud in my head. How would you read this symbol? How about kickboard, like ones you use in a pool? I love the idea of saying kickboard. I admit that I've just been saying box. And when I do this with my students, I draw that box in green and then I call it green box. But that is not the case here because it's in black and white. Secondly, it might be difficult for people who can't see green. And so I love the idea of kickboard. Read it however you like. Okay, so the next question is about A plus B. So this is on page 84. I said, it's important to note that A kickboards B. Yes, so maybe when we pronounce that word, we should make sure it's a verb because it is a verb. Because A kickboards B is a statement with a verb in it. And so it can be true or false, whereas plus is a binary operation. So A plus B is not a statement because it has no verb. So this question is, could there be a sense in which we can think of it as having a verb? And I think the answer to that is sort of, but not technically, because the point I'm making here is about the use of that formal symbol. And when we use that formal symbol in formal mathematics, it is very crucial that it does not have a verb. It's a binary operation, which means that A plus B, whatever A and B, whatever type of thing A and B are, A plus B is another of those things. It is not a statement. And that's really important in the formality of the mathematics. And so you can think of it as implying a verb, but it's really important that when you interpret that the symbols formally, it really doesn't have a verb. The next question on page 85. Oh, it's just a thanks. I really like the paragraph following example 7.2. This is about how you prove a for all statement. And it says it's helpful being able to share that type of thinking with other people not familiar with proofs. Thank you. Oh, I'm thirsty. I need some water. I'm glad that you appreciated that. I think it's really important to share that kind of thought process as well. Page 87. Yes. And there's a lot of negatives in this question. Is the always false for example 7.5 slightly different from things to think about 7.2 because it is not true that the implication is always false? And what is always false is, okay, so there's a lot of negatives in this. So I'm going to go to the whiteboard so that I can write some things down and see if I can clarify what's going on here. Okay, so the point seems to be that when we did reflexivity, so we're thinking about the relation less than on the real numbers. So for reflexivity, would say, for reflexivity, it would say, for all, have I introduced the for all symbol? Yes, I have. For all, what symbol did I use? A. For all A in R, A is less than A. So non-reflexivity is the negation of that. And to negate a for all statement, you just say there exists. So that would say there exists A in the reals such that A is not less than A. Now, if A is not less than A, that means that A is greater than or equal to A. A is not less than A. And what we've actually got is much stronger than this. We have something more. Because we have for all A in the reals So that's the sense in which the reflexivity one is extreme. And the question then was about the symmetry one and whether that's different. So symmetry would say for all, let me get the same notation, for all A and B in the reals, A being less than B implies B being less than A. So non-symmetry, we just negate that. So that would say there exists A and B in the reals such that A being less than B does not imply B being less than A. And so in fact, we have something more, because we have for all A and B in R, A is less than B does not imply B is less than A. So up here, I could have written this as A is not less than A. So for all A and R, we have A is not less than A. So what I'm trying to say is that up until this point, these three statements are analogous to these three statements. So if I change color for a second, then what I'm saying is that this statement here, what letter should I, statement 1 is analogous to statement 1 here. We've just switched reflexivity for symmetry. So statement 2 is just a statement of non-reflexivity. So that's analogous to this statement of non-symmetry. And then statement 3 is that we have something more where we have it for all rather than just exists. But in the case of symmetry, we have something even more extreme than this, because we have something even more. We have even more. Because we don't just have A less than B doesn't imply B less than A. We have that A less than B implies that B is not less than A. It actually can't be true. So this is something that may need a little bit of clarification. We have, if this statement is P and that statement is Q, then what we've done is we've taken P implies Q and we've negated it to say P does not imply Q. But just because P doesn't imply Q, it doesn't mean that P implies the actual opposite of Q. P could just not necessarily imply, P just doesn't imply Q, but P implies not Q is something different. And so what we have is even more, because we've got for all A and B in the reals, A less than B actually implies that B is not less than A. This is stronger. So what we have is a series of statements that get stronger and stronger. So non-symmetry is quite a mild statement. This is a stronger statement, and this is an even stronger statement. So we have a very extreme kind of non-symmetry here. And let me just clarify that thing about negating an implication. Let me move the whiteboard up a little bit. So note, P implies, let me see if I can do this. P implies Q means whenever P is true, Q is true. P does not imply Q means it sort of might happen sometimes. P does not imply Q means it is not the case that P forces Q to be true, right? P might not force Q to do anything. So for example, P and Q might be completely unrelated. For example, if P is being a cat and Q is being black, right? Being a cat doesn't imply that you are black, right? There are lots of different colors of cat, but at the same time, P doesn't imply not Q. So P, being a cat doesn't imply that you're not black either. So P implies not Q means whenever P is true, Q is actually false. So those are two different ways in which P doesn't imply Q. So this is, again, a stronger statement. This bottom statement is a more extreme way of P not implying Q. And that's the one that we've got here. These things do get a bit convoluted. And if you do formal logic, then what we do in formal logic is we express implication by means of and not statements. So this may be a bit much, but I'll just say it anyway in case you're interested. So in formal logic, P implies Q is defined to be the statement. Let me see if I can get this right. So what we're saying is that it is not possible for P to be true at the same time as Q being false. Hopefully I got that right. So this symbol means and this symbol means not. So P implies Q means it is not possible to have P being true at the same time as Q being false. If P is false, anything is possible. It doesn't tell us anything. So that means that P does not imply Q is the statement, it is not true that P implies Q. So we negate this whole statement. And what we get is, if you do not, then the nots cancel out. So we just get, there is some situation in which P is true and not Q is also true. Did I do that right? So, but at the same time, P implies not Q. Well, now we've got to put not Q into here. So what we get is not P and not Q, which is the same as saying not P and Q, right? So these two things are different. And I'm just going to pause the video now to make sure I did this right. Okay, I've seen what has just got me a little bit perplexed. And so I assume it has got you perplexed as well, since it's got me perplexed. And it's the fact that I've probably got myself in a bit too deep trying to do the implication in propositional logic without talking enough about logic. So possibly ignore that part if you're not following. The main thing I was trying to show is the difference between negating an implication and actually implying a falsehood. But the thing that I've confused myself about here is what the negation of implication is. Because what I seem to have said is that P does not imply Q means literally that P is actually true and also that not Q is true. But what it might mean in practice is that there exists an interpretation of the structure in which P is true and Q is false, not that it's always the case. And so if you didn't follow this bit from here, then I encourage you to just take that part. And so I'll say the slightly more informal part again. So we'll just ignore that part for a bit. And we'll use the example, being a cat does not imply being called pause, right? But also being a cat does not imply not being called pause. So we have two slightly different statements there, and implying the negation is much stronger than just not implying the thing. And so what we had in this symmetry case was that we actually implied the negation, which is much stronger than just not implying the thing. In the reflexivity case, there was no implication going on, and so there was no stronger statement to make here. So that was a very long way of saying that there is a slight difference between those situations. Okay, good. What is the next question? The next question is, of the three conditions for an equivalence relation, transitivity seems like the one that most clearly speaks to the concept of preserving structure. Does transitivity play a special role in category theory? The generalization of transitivity does play a very important role in category theory because that's what composition is. But the preservation of structure in category theory could be argued to be more about functors, which is morphisms between categories than morphism inside categories. But yes, it's true that transitivity is going to generalize to composition of morphisms, and that is a really important aspect of category theory. So the next question on page 89, is the mother of is not a transitive relation. However, the similar relation is the genetic ancestor of is a transitive relation. Are there mathematically interesting examples of taking a non-transitive relation and slightly adjusting it so that it becomes a transitive relation? That's a good question. There definitely are examples. Whether they're mathematically interesting or not, I don't know. But I can think of examples where we slightly relax conditions in order to let more things happen. Whether it's transitivity or not, I couldn't say for sure. So the thing that I thought of immediately is modular arithmetic. So if you're doing arithmetic mod n, then what you're interested in is when numbers have a difference that is divisible by n. And you can generate it by saying, so if we're doing arithmetic mod 5, then we could say, well, 3 is congruent to 5 because the difference between them is 5. And 8 is congruent to 13 because the difference between those is 5. But that is not a transitive relation because the difference between 3 and 13 is not 5, it is 10. And so in a way, that's like the genetic ancestor of. Instead of saying specifically it has to be exactly 5, then we can say as long as it is some multiple of 5, then it's okay. Yeah, so maybe that is a mathematically interesting example. Good. And then finally, there's a general question: can I use category theory to have a think about relationalism philosophy? This person heard this idea from physicists like Carla Rovelli, Lee Smolin, and John Byers. Well, John Byers, as we all know, knows a lot of category theory, and so I'm not surprised that he talks about relationalism philosophy. The idea is, so I didn't know anything about this. I know very little philosophy, except that it involves a lot of isms, any of which I can believe in any given moment. And it's the idea that the world is not made of objects and substances, but is made of events and relations between events. and processes that create these events. Is there a specific connection to category theory? So I confess I just Googled it. And as I said last time, I encourage you to Google things as well, because if all that happens when you ask me a question is that I Google it, then maybe it's something that you could have Googled. And I say that to encourage you to believe that Google can be your friend in helping you learning things. And so I Googled it and discovered that John Byers, yes, does talk about category theory as a way of expressing relationalism formally. I would say that category theory isn't declaring that the world is made of relations. It is saying that this is an illuminating way of thinking about it. And one of the things that I always find a bit strange about philosophy is that philosophical theories seem to declare this is what the world is made of. Whereas I think there are many different illuminating ways to think of the world, and whatever can be illuminating, we can try and get what illumination we can out of it. And so this question continues to say, is there a specific structure in category theory that is about events? Are the objects in a category actually best understood as events? So that I would say no, because the objects in a category can be anything. And the whole point is that they don't need to have any intrinsic characteristics. And so if we tried to declare that they were events, we would be giving them some intrinsic characteristics. The power of category theory, one of the aspects of its power, comes from the fact that the objects in a category can be anything. So we don't need to think about them in any particular way, and it's better not to, so that we can remain open to the possibility that they are really anything. Is relation anything like correlation, or is it more than that? It's more than that, because the relations in category theory also can be anything. All they have to do is satisfy some axioms, which we will see in the next chapter. But aside from that, they really can be anything, which is why we try to call them things like morphisms or arrows rather than maps, because map is already a bit suggestive. Maybe morphism is suggestive too. But the objects and the morphisms can be anything as long as they satisfy the axioms of a category. So I would encourage you to not try and interpret them as specific things, but to remain open to the possibility of interpreting them as many things. Good. And so some final appreciation. Thanks in advance for taking the time to answer these questions. Well, thank you for sending in the questions. And someone else says, I'm still catching up to the book club, but want to say thank you for hosting this. You're very welcome. And finally, thank you to Julia, Tim, and to me for all the time and effort that goes into administrating, editing, writing, and recording the book club. Well, thank you. Yes, Julia and Tim are doing great work in sorting out the questions and sorting out and editing the videos. And so thank you all very much. Excitingly, we're getting on to the definition of a category in the next chapter, chapter 8. So I look forward to seeing your questions and hope to see you there. Bye.